I'm Andrew Neverman, another geomorphologist here at Haunui, and I'm talking about some work we've been doing in the Haunui research catchment, looking at earthflow dynamics and their sediment load contributions in a headwater catchment. So firstly, why did we want to study earthflows? And they occur throughout New Zealand's soft rock hill country, and they can range anywhere from 2 to 10 metres deep and may exceed 100 hectares in area, so could possibly have quite a large volume of sediment to deliver. And they're most prominent on crushed mudstone and argillite, and therefore tend to produce quite fine-grained material, which when it enters a stream network attenuates light, producing visual clarity issues. And degraded visual clarity, of course, impacts aquatic biota. It can also have cultural and recreational impact, such as affecting swimmability or removing timeless species. So our particular research objectives for this project were to better understand the spatial and temporal patterns and the hydroclimatic drivers of earthflow movement to help us better model them. So that's what is driving the movement, and then how does that vary through space and time. We also wanted to better understand the contribution of earthflows to the catchment sediment budgets, and therefore their potential impact on water quality issues. So we needed to get a handle on the magnitude of sediment contribution and the timing of that relative to other erosion processes. So our study catchment for this is the Haunui research catchment. It's about a 20 square kilometre catchment in the hill country. It sits in the Turumea River in headwaters, which is a tributary of the Manawatu. If you don't know, you're currently located in the Manawatu catchment. The catchment itself is about 20 square kilometres. We're monitoring turbidity and stage to get load continuously at the outlet, and the earthflow in question is upstream of that outlet. We've established a range of instrumentation through the catchment. This includes doing multi-temporal surveys, so yearly, with a GPS to monitor or measure the movement of these waratahs in earthflow. And we're combining that with drone surveys to reproduce the surface of the earthflow at each year, which we can difference to get an erosion volume. We have a continuous GPS operating on the earthflow, and that records every 30 seconds. It's been running for about 3 years, so it's produced a lot of measurements of where the earthflow is, so we can track movement through time, sub-daily. We've installed piezometers in the earthflow, so these are drilled right down to the inferred failure plane, so we're looking through the whole earthflow body, and that's recording the piezometric head of the water in the base of the earthflow to look at pore pressures. We also have a meteorology station recording things like rainfall, temperature, humidity, and wind speed at the monitoring outlet, along with continuous turbidity modelling to get an estimate of sediment loads. So in terms of the movement dynamics and drivers of the earthflow, looking at some of the drone surface models here, we can see the earthflow through time is moving downhill towards the stream. So just to get your eye on the movement directions. Over the approximately 4 years of monitoring PEG surveys, we've recorded up to about 35 metres of displacement downhill. That movement is varied throughout the earthflow, where we have this zone in the toe of much higher movements, with slower movements in the sort of mid and upper section of the earthflow. We've got the main earthflow body here, with some sort of side movement here of much lower rates, and this almost stable landslide block at the top here. Looking across the 4 survey years, we see about a 2 to 3-fold variation in movement rates. We've had as low as 3 or 4 metres in the toe, and in the last year we've had up to sort of 12, 15 metres. There's quite a bit of annual variability in the earthflow itself, and those relative patterns of the zones are faster in the toe, slower in the middle, slower again at the head, hold across most of those years. In terms of the temporal dynamics, this is where the continuous GPS comes in. And we've got this time series from about December 2019 to March 2023. And this is showing the cumulative movement. So over that time, we've had almost 30 meters displacement on that continuous GPS. And down the bottom, we can see the daily movement. So those spikes are showing when movement has occurred that exceeds the uncertainty on the GPS. What we really see here is these distinct phases of stability in the blue and movement, which is almost continuous, in the red. And you'll see they're roughly 6 months stable, 6 months mobile. And the grey shading is the sort of October to April, so expected to be drier, and white is the more winter, April through to October. So looking at the groundwater piezometric pressure and rainfall in relation to the daily movement, what we see is a lot of this movement's occurring while the groundwater piezometric head exceeds a threshold of about 1.8 meters. So threshold's a little bit very specific to this earthflow, but what it's showing is you need that higher groundwater pressure to drive the movement. We have days, periods in here where we have some high rainfall, but no movement when pore pressures are low. So if we compare the daily movement to the daily piezometric head, modelled soil moisture deficit and rainfall, what we have here is the grey dots are showing days when the GPS wasn't really moving. There's just a little bit of noise in the GPS signal, and black dots when that movement exceeds our level of detection, so we're confident there's movement. And we see most of the movement occurs above 1.8 meters of that piezometric head, or when the soils are getting near saturated. And in fact, those thresholds occur for about 50% of the time, but you get 97% of the movement when you're above those thresholds. The relationship with rainfall looks a lot more scattered here. We have our highest day of rainfall, which had undetectable measurement on the GPS. There's some plots here of lag plots. So the y-axis is the correlation coefficient between daily displacement and the piezometric head on the top, daily displacement and rainfall on the bottom. So you see here's larger bars for the relationship between piezometric head and displacement, so a stronger relationship at the daily scale. On the rainfall, low relationship, but you see a bit of a lag here. So around 3 to 4 days following rainfall, you're getting a stronger relationship with movement. Over on the side, we have cumulative displacement, so the total movement over 28 days compared to the mean piezometric head over 28 days, and we're seeing a stronger relationship than with that daily movement. Same for the rainfall down the bottom, strong relationship as we start to look over longer time windows, and we're also seeing that lag response. But of course, as we accumulate rainfall, that starts to drive our higher piezometric heads, so there's some correlation there. Just as an example of rainfall versus piezometric head here, we have a month time series. We had a large rainfall event of 5 days with up to 100 mil rainfall on one day. This drove a response in the piezometric pressure with rising groundwater in the earthflow, higher pressures, and on this day here it crossed that 1.8 meter threshold, which triggered increase in the velocity and displacement on the earthflow. So grey dots, again, undetectable movement on the GPS, black detectable, and you'll see that movement sustained whilst the piezometric head is high. So there is a shared relationship between rainfall driving that piezometric head triggering movement, but that higher pressure sustaining the velocity. In terms of the sediment load contributions, we've got these 4 drone surveys, so we can difference the surfaces to look at where erosion or deposition occurs within the earthflow. What we're seeing is a lot of erosion upslope, transitioning into deposition at the toe. We have particularly high deposition right at the toe where the earthflow is actually pushing out into the stream. So it's not stationary, it is moving into the stream. So the stream isn't competent enough to fully erode what's being deposited at the toe through these 3 years. We've got about a magnitude difference in the eroded volume across the 3 years we've been monitoring. So anywhere from 1,200 to 11,000 cubic meters of sediment lost from the earthflow to the stream network. Comparing that to the catchment, to the load, suspended sediment load measured at the catchment outlet, the earthflows contributed equivalent to anywhere from 14 to 44% of that catchment load, and overall a total of about 28%. So to summarize the key findings from this, that piezometric pressure at the failure surface was a primary driver for displacement on the earthflow. Displacement was continuous through the wet periods of winter and spring, and remained elevated while that piezometric head was high. Rainfall events during that period accelerate movement, but equivalent rainfall over the drier summer months when piezometric pressure is low does not trigger movement. The total movement on the earthflow then is a product of the magnitude and distribution of that rainfall. If most of that rainfall falls during winter, when the groundwater levels are high, you're going to get much more movement. And if that total rainfall is spread out more through the year and occurred when groundwater levels were lower. Earthflows may be significant sources of fine sediment then, whilst soils remain saturated for longer periods, and in the absence of higher magnitude storms that are triggering the other processes such as shallow landslides and riverbank erosion. If we were to look at mitigating these earthflows, we should be looking at reducing water in the earthflow body. And changes in earthflow movement in future are likely to be driven by changes in the magnitude and distribution of rainfall.